Okay, so let's start up. I want to take 5 to 10 minutes before I turn over the microphone to Katerina to finish up one topic that we didn't have time to cover last time. So we're talking about exploration versus exploitation. And, we talked about a number of approaches. I just want to end up by saying there are even more approaches. And one that's kind of easy to describe is called probability matching. And the idea is simply this. If you take a probabilistic Bayesian approach to the question of what's the best way to trade off exploration and exploitation, one way you can do it is say, well, you just want your policy, pi, to always choose the action that is in expectation has the highest probability of being the best action. So that means given your experience, ht, all the rewards and states and actions you've taken up till time t, let's just say that with you're going to assign to each action a probability that you'll choose it, which is just equal to the probability that it's the best action, the action that has the best Q value. So that's a very kind of obvious way to look at the question. And if you think about it, and this will be maybe more clear when we look at one simple example, it turns out that this approach is naturally optimistic in the face of uncertainty. That is, if you are unsure exactly what the Q value is, so you have some distribution of possible Q values for an action, then if you have some Q values where you know a lot, and so you have a very tight distribution, and others where you have a very broad distribution, then the broad ones are going to kind of be have some significant probability, because the distribution is so broad, that they're the best action. And so in that sense, it's kind of it just kind of follows from this simple and kind of obvious principle that you're going to end up being optimistic and choose ones where you have more uncertainty. Now, practically, this can be somewhat of a problem, but just to get the idea across, Thompson sampling is one instantiation of this idea, and I just want to illustrate it here. So again, the principle we're trying to follow is to assign to each action, our policy, to assign a probability which is equal to the probability that it's the best action. And so what that really means is if we have some probability distribution on rewards, pay no attention to this floating R. If we have some probability distribution R on rewards, then what we want is the probability that this is the best action is just the expected value over that reward function of it being the best action. And so to illustrate this, suppose that in fact we have some assumed parametric form for the reward function. Suppose, for example, we think it's a Gaussian reward function. That is, for each action, there's a mean and a standard deviation that defines the distribution of rewards that we'll get for that action. And of course, suppose we don't know what that reward distribution is, but it exists out there. And so if we assume, for example, that it's Gaussian, then we can use Bayes' law to compute, to estimate that Gaussian reward distribution. Now, if we're going to estimate a Gaussian reward distribution, what are the parameters we need to estimate? Right, giveaway question, just to make sure you're not sleeping. We have to estimate the mean and the variance for the Gaussian for each action. And instead of, if we're Bayesian, then instead of getting a maximum likelihood estimate of that, we might have some priors on what we think that mean and variance is for each action. And then we collect some experience. HT, again, is the sequence of rewards and actions and states that we observe. Given that, then we can get a posterior distribution on the parameters of that reward function. So we can get an posterior estimate of the mean and the variance associated with the reward distribution for each action. Now, suppose, just to illustrate, this plot up in the right-hand corner is our estimate, say, for the mu's. Suppose we have 3 actions, and having seen some experience, we now estimate that the mean for action blue, red, and green are the 3 means shown there. But of course, we're uncertain what those means are. We have just a distribution over those, right? And we have a similar distribution for the variances, let's say the sigmas that define those 3 reward functions for the red, green, and blue actions. Then the idea of Thompson sampling is that we can basically sample to estimate these expected values by doing the following thing. We take the current parameters that or the current distribution over parameters that we have as a Bayesian, as we're trying to estimate the mu's and sigmas for the reward functions. And we just sample that. We sample a reward distribution from our posteriors on the mu and sigma parameters. So that means, for example, we'll pick a green mu and a red mu and a blue mu by sampling those 3 distributions that we have on the mu's. And similarly, we'll sample a red, blue, and green sigma. And then given that sampled reward distribution, now we actually can say, well, given that we've chosen these mu's and sigmas, here are the reward distributions. And then we can simply solve for what would be the best, or what would be the Q value under that sample. And if we sample repeatedly, of course, it's an unbiased, it'll give us an estimate of the expected value of the Q value for the action, where that expectation is taken now over the uncertainty that we have about what the reward distribution really is. And then we just choose the maximum action according to the sample that we've drawn, and we take it. Okay, so you can see, and we can sample more times if we want to have better estimates, or we can sample fewer times and just take more actions. But you get the idea. So what this is doing is really taking into account more explicitly as a Bayesian what is the most likely reward distribution given the data, but what's the distribution over reward distributions given the data. And then sampling that is a way of turning that into action. Yes?
So do you pick Gaussian distributions because in practice they happen to be good, or is it just because the math is easy?
The math is mighty easy, and I wasn't going to state that those were Gaussians. They're just shapes.
All right.
Some people try to rationalize these things by things like the law of large numbers and more mechanistic explanations of how rewards get generated. But the truth is that's very different in different domains. And so in general, it's hard to justify. But mathematically, it is easier.
So in practice, should we use Gaussians, or do we need to look for multiple shapes?
I don't know the answer to that, and my guess is that Katerina knows that answer better than I do when it comes to robotics applications. But B, I'm sure you can come up with domains where it's a very reasonable thing to do, and I bet if you put your mind to it, you can come up to with domains where it's a obviously boneheaded thing. But the idea is that there, be some parametric form that we're assuming for this distribution, and then we can get the posterior over the parameters of that distribution and sample that posterior, which is a way of really sampling distributions. And so it takes into account properly the true uncertainty that we have about the reward function that we're trying to choose actions, design a policy for. Okay? So anyway, that was the idea that we didn't get to talk about last time. I think it's a useful idea. In fact, we'll see that it's a useful idea. And so I just want to summarize then. Here are the kinds of approaches we've talked about, -1. So we talked about epsilon greedy approaches, ways of being explicitly optimistic, either by initializing all of our Q values not as 0, but as some large optimistic value, which we noticed is the equivalent of putting a Bayesian prior on what those Q values are. We talked about taking into account uncertainty by using upper confidence bounds rather than the most probable value according to the distribution. And probability matching is what we just talked about here, the Thompson sampling being an example of that. There is one other idea, I'll just mention it verbally, and you'll love this idea because it's exactly, if you were a truly dedicated MDP person, the way you would think of the problem. We can actually define an MDP to take into account the information that we have from our history. Now, maybe I'll show you this slide. It's a little easier to. Here's the idea. The motivation is we'd like to, if we're going to do reasoning about exploration versus exploitation, we'd really like to use all of the information available. And so as an MDP person, one way you can do that is say, if you give me an MDP, which has state S, I'm going to define a new MDP, S tilde, S squiggle hat, which is concatenation of the state you gave me, plus a summary of my history, the accumulated information that I have. And then I can say that in my transformed MDP, the next state function maps, given an action in a new state, which is literally the pair, maps to a new paired state. And now my next state function, the model that I'm trying to learn here, actually can predict, or would predict if it was known, not just the change to the physical state, S, that you gave me, but also the change to my information state, how much more I will know if I take this action. So it's a way of trying to explicitly model the information value of taking this action, not just the reward in your original ground MDP. And then, of course, I need to define an appropriate reward function to go along with that. But so then it just gives me a different MDP. And the policy that I want to think about now is one that will maximize some reward over some interval. But that's explicitly now explicitly making the information that I know and the expected information that I'll know if I take this action part of the MDP itself. So it's kind of an elegant, beautiful idea, and it's like what you would do if you never thought of anything in your life except MDPs. So it's an interesting one to kind of have in the back of your head. Okay, so with that, let me turn it over to Katerina. Any questions while she's setting up? Yes. All of them would be the default. So that'll force you to essentially explore all of them over time. If you had some prior knowledge that made you think that, action 4 is really not very good, then you might not initialize that. Oh, quick statement. I need to leave early today, so I won't be available for office hours today, but I will on Monday.
So we will discuss now about how can we use exploration, the ideas we have just seen, with functional approximation in large continuous state spaces. So let's visit the basic exploration ideas we have seen so far. First of all is epsilon greedy. This we knew already before entering the exploration lectures. It's something we've been using all along. And because we've been using it all along, we know that it can be used with large continuous state spaces. We saw the upper confidence bound that tells us how to choose the action based on how many times you have visited a particular action. Okay, so we count actions and we see how it comes from this Henderson inequality. And Tom just discussed about Thompson sampling, where instead of just keeping track of the mean rewards, you keep track of the full distribution of the mean rewards and sample from this distribution. So when we want to take these ideas now to large continuous state spaces, we have the following problems. First of all, we need to generalize the notion of counts. Well, because we had bandits, if you remember, those counts did not depend on states. So now we'll be counting state, action, occurrences. Now the problem is that once we go beyond tabular methods, how do we count? In the real world, we will never see the same state again, okay? So counting when exactly you've seen the same state will be meaningless because this will always be 0. So we'll need to design a notion of similarity between our states, and we'll see a couple of different ways that you can take exactly the same, upper confidence bound, and instead of this NTAC, which is mere counting in our case, you'll be these pseudo counts that we'll come up with. Then the question is, how do we take the idea of Thompson sampling in general MDPs, okay, beyond bandits? We want to keep track of a distribution, okay, of our model parameters. Our model in bandits was the rewards, the mean rewards of the different bandits. In general, how do we generalize this in a general Markov decision process? We need to discuss about distributions over Q functions. So far, we would only have one critic, if you remember. We would always be building one Q function approximation. What is the problem with what we've done so far? And the most interesting part of the lecture is in the middle, is some idea that we didn't see in the previous lecture. How do you use transition dynamics? And how do you build a model of the world as you go along? And how you can use it to get exploration rewards. Okay? And we will see this in extreme, where we throw away the task relevant rewards, and we only use curiosity rewards coming from this transition dynamics, and we still can solve some tasks, which means that curiosity correlates well with task relevant rewards. You'll do well if you don't get stuck all the time at the same point. Now, what I want to mention is to be able to explore, You really need to know what you don't know. Okay, that's why keeping track of a distribution is important. Because if I just give you 3 mean estimates of the rewards of the bandits, you don't know which estimates are a tall and thin Gaussian, and some are short and fat Gaussian, right, which has a lot of uncertainty. So if you don't know for which bandit you're certain and which bandit you're uncertain, you don't know how to guide your exploration. This is exactly the problem. So we do want to represent our uncertainty. And we'll see how can we represent this uncertainty. I mean, in the case of bandits was easy. We'll see how we can do this with Q functions. Okay? And exploration, efficient exploration, all has to do with how do you keep track of your uncertainty in your Q function, in your transition dynamics, on your policies, on the states that you have visited and that you have not visited. Okay? And you try to visit and the part of the state that will minimize essentially your uncertainty. So let's make this concrete. This is what we just discussed, okay? You want to keep a posterior distribution of the mean rewards of the bandits and sample from it. Once you sample those variables, then you just act, as if they're the truth, all right? So essentially, you pick the bandit with whom you have the highest mean reward, and then you take this new data point and you update your distribution, all right? No epsilon greedy here. Just because you keep track of the distribution, just sampling from it, you don't need to add extra noise. Okay, so that's the beauty. So how do we generalize this? Well, we need to keep, the equivalent is exactly this. We don't have one single Q function. We have a distribution, okay, over Q functions. We sample one Q function. We think that this is the golden correct true Q function, and throughout the rest of the episode, we just act under this Q function by maximizing the Q values. We take the tuples, the experience tuples, and we update the whole distribution, okay? All the Q, this distribution set of Qs is updated. This is off policy, so it doesn't matter which one you use to correct those experience tuples. The whole distribution will be updated. Now the question, of course, is how do you keep track of a distribution of Q functions? Yes?
Maybe we'll answer this later, but why do you choose a Q function for a single episode instead of like for every action, for example?
What you're saying, so I think your question is why instead of sampling actions from epsilon greedy, don't I just sample for every time step of every episode a new Q function? It just, right, instead of, committing on one Q function for the whole episode.
Yeah.
So committing, so this is exactly the benefit of using such distribution over Q functions instead of epsilon greedy. This noise is undirected, while at least the Q that you will commit for multiple time steps following it, okay, you will be able to see much further that even in every time step, the noise is picked up independently.
Well, I guess without the epsilon greedy though, you could still sample a new Q function for every time step.
Yes, you can, but then again, the noise is independent. You don't want independent noise. You want to say, okay, what if this is my Q? Then what this Q thinks about the world? Oh, then I need to potentially explore this. Because if one Q sends you this and the other sends you there, then again, you don't have, as we say, deep exploration, deep for like many time steps.
Okay.
Okay.
That makes sense.
All right, so here's the thing. There are many solutions to this problem. Some are beautiful and principled, but they don't work well. And some are less beautiful and less principled, but they're easier to implement, and in practice they work better and people use them. However, I think this problem is very important. So we should think about this case. Let's make this concrete. Imagine that your data points are those black crosses, okay? So this is the X, this axis is the X-axis, and the Y-axis. And you are trying to fit a regression network to those data points, okay? And then you query this network and you say, okay, what is your value for this X? And the network returns you this red line, okay? Now you have no clue of whether you should trust your prediction or not, okay? And there is no reason why would you trust your prediction beyond the regime that you have any data, any evidence, okay? Now the question is, we do want a way to know when we're uncertain. And we'll make the connection to the Q straight away. So the problem, this problem arises because your weights, you have only used one point estimate for your weights. You didn't keep track of the full distribution of the weights. Under this training set, many neural networks would have fitted it perfectly. Okay? However, you committed in one of them. Now, not only you don't know when you should trust it or not, but probably you also have overfitted like crazy. And why I like this Bayesian, let's say, view of neural networks, despite the fact that so far, empirically, is not used. Why? Because it has not underperformed dropout, which is just random masking of weights, which probably you know from previous courses that you've taken. But it's the principal way to manage overfitting. You say, I have this labeled set, and I'm just going to change the weights from my prior distribution so as I fit the training set. But other than that, I'm going to have as high entropy on my weights as possible. Okay? And then you only need to change one knob to control your overfitting. How well you fit your training set versus how well you follow distribution. No, well, let me show this. The prior distribution of the weights. So here is how a Bayesian neural network looks like. Every weight is a small distribution. Now, this doesn't cost you much more parameters. To parameters that say a single weight, instead of using one scalar, you may use one mean and one standard deviation, 2 extra values, for example. Okay? So now if you want mixtures, okay, a few more values, but it's not that much more. All right? And the beauty is that once you sample those weights, while all of them agree when there is data, they disagree in the regime where you don't have evidence. They disagree. So then you can look at the entropy of those predictions and realize that, oh, I really don't know, what happens here. I should not trust my prediction. Okay? Now, how is this related to your Q? Okay, it is related in the following way. When you don't know, the part of the set you don't know, the Q functions will all disagree. Okay? This means what? That they all guide you in exploring all different directions. Okay, so this is good. I do want to explore when I don't know. However, in the part of the space where you know what's happening, all Q functions will, suggest the same actions. So then you're going to be exploiting. All right? So you explore and exploit based on your uncertainty, which is much better than epsilon greedy. Okay? So this is good. This is good. Now, as we said, there are multiple ways you can do this. So I do have later in this lecture a couple of slides on variational inference for Bayesian nets. If you guys are interested, we can totally organize a recitation on variational inference, both for Bayesian neural networks as well as latent variable models like variational autoencoders, mostly because they come, again, in fact, they're going to come later in this lecture. So I'm not exactly sure how much time we're going to have. That's why if we don't have time in this lecture, we can totally take this part in the recitation. Now, what I want to discuss is the following. There are many ways that you can do better than just having a single Q function. The best one, the most principled one, is to train a Bayesian Q function, all right? Where the weights, instead of being estimates, they're distributions. Then you sample from those, exactly what you did with the bandits, and you commit on the thing that you sampled for the whole episode. You take the tuples that you collected, you update your Bayesian network, and you continue. Now, the second point, which, at least in computer vision people use a lot, are ensembles. Instead of training a single network, train multiple of them on different subsets of the data. Now, apart from using different subsets of the data, you can also use different weight initializations to encourage diversity between them. So then, when you are to make a prediction, okay, you can look at the entropy of all this ensemble set. Now, for Q function, you're just going to sample one of those guys, exactly the same thing that you would do by sampling weights. Is that clear? Now, training multiple models is computationally inefficient. Apart from that, having data to be completely different in each other is also data inefficient. So an approximation to the ensembles is this type of architecture where there is a backbone that is trained with the whole data, but there are multiple heads, which are trained with different subsets of data. Okay? So again, to sample a Q function, you just sample a head, and you just trust that head. And this is exactly what we're going to see in this bootstrap DQN paper. And the most weak way to do ensemblings is by training with dropout, randomly switching on and off weights. Okay, randomly switch off weights. When you switch off weights, you have a new neural network, right? So it's as if during training, you're training multiple ensembles, completely randomized. Now at test time, people do this for regularization, and at test time, they switch off dropout. And they say, okay, here is your network. Now, if you want to see the entropy and figure out the uncertainty of your prediction, you need to switch on dropout also at test time. Take the ensemble and look at the entropy of your predictions. Okay? Okay. So this is exactly what we want. We want, when we have data, actually, this green and blue goes with the next. This is exactly what we said. So the entropy is high in the no data regime, okay? Then the Q function values have high entropy. They will encourage exploration, will send you in different places. Otherwise, when the Q values have low entropy, then I exploit, I do not explore. They all suggest the same. And important thing is that we're not using epsilon greedy here, right? We are exploring because we keep track of multiple Q functions. So here are the results. And yes, you do better if you use bootstrap DQN as opposed to using a standard DQN with epsilon greedy. You see the scores are in general better for different games. And here comes the difficult game where nobody can score because the rewards are extremely sparse. Okay? Usually in Atari games, as soon as you hit something or you hit a wall or something, there is a reward up in the screen that all the time rewards you of what happens. So you get very dense rewards. In some cases, the rewards are very sparse. You need to go, find the key, put the key in the door, and then you get something. Does this make sense? So now, for you to go to pick up the key and put it in the door, there is nothing to guide you to do this, okay? That's why it's important, to gather knowledge that, keys go to doors. The agent doesn't know anything about this, okay? So that's why building a model of the world is important. Yes.
Second picture, why it's so lower than the green in the end. For frostbite.
Yes. Why at the end the reward goes down, right? Instead of going all the way up. So I think there's something wrong here. Overall, the more you train, the better policies you get. Does this make sense? Except if there's some weird collapse. Okay, so what you do is you do random seeds, and the normal curve would be the more you train, the more data you get, the higher score you obtain. Okay, so let me check about this and get back to you, either next week or Friday, depending when we're going to meet again.
And in our experience for training the network,
yes,
we find that after it goes a high point, it may go down pretty quick in sometimes, similar with this picture. So
the policy will collapse.
When it achieve or win the game, and then it will crash. And I'm wondering, is there any theory or mathematical explanation for this situation in reinforcement learning?
Yes. So for which in particular part of the homework you're talking about?
Homework. Yeah, exactly.
So you'll train the network and then it will collapse.
It behaves pretty well after a training, and then suddenly it crashed. It cannot do anything.
In more advanced levels of the game, let's say.
Yeah, as the same with the pictures. So yeah. So I'm wondering, is there any research on that?
But
problem?
1 second, I want to ask you, when you say it crashed, in which level it crashed, let's say? In which level? Let's say, yes. So things that before you were able to solve, then you cannot solve them, or you go in the new environments and...
I already achieved like 200, right? And then it goes down to minus 200.
So
I
more
see.
training data, it just drops. I mean, I think we all have this experience. Things are climbing up, it's getting better, and then it just drops, right?
Yeah.
And sometimes it never recovers, or sometimes it drops to zero, comes back up again, and then drops again, and it just keeps going up and down.
I see. What if it has to do with the way you sample your data? Does this make sense? You may be sampling, you're fitting this queue all the time, right? Let's say. what if the way you sample your data, you forget the important points? There are some important points you need to get right, but as there is more data, if you do blind sampling, because let me tell you, you have a lot of data tuples. Some data tuples will generate an error signal to you, will give you some gradient signal to improve, and some others will not, right? But this shouldn't hurt you, except if these normalizations are the problem. Because when you feed data tuples that don't have anything to learn from, then your policy just shouldn't change, right?
And in this situation, they just explore the certain action, right?
Yes.
Based on the uncertainty. But on that picture, it go down too. So I'm wondering.
Let's see some other. So I'll check all this and I'll reply on Piazza on this question, since you all have this one. Okay, so 1 second. So here is the intrinsics. This is what we've been using all along in the course. And what we'll see now is we're going to add something. We're going to add an exploration bonus, okay? We're going to add an exploration bonus. So this is very simple because then you just take the reward exactly the same way you had it and you just put it in your favorite model-free algorithm. You don't change anything. The only thing we'll discuss is how we'll compute this exploration bonus reward. Maybe two things you need to be paying attention. One is the weight that you put in front of that exploration bonus. And the other very important thing is the following. Extrinsic rewards are always the same. Same state actions, next states will always give you the same extrinsic reward, okay? However, the exploration bonuses are changing. They are non-stationary because what is new now, it becomes old and known later, okay? Do you see? So throughout training your policy, while the extrinsic reward is all the time the same, the exploration reward changes. Now, how do you deal with this? Well, what I've seen in many papers is the following. Instead of just using the TD0 as your critic, you're trying to train your critic, and usually we take reward plus gamma Q, okay, to try to regress against. Now, because this Q changes slowly, your Q changes slowly with gradient descent. It may not be able to reflect those fast-changing rewards. So what you do is you mix. You take the TD, it gives you some reward. You take the Monte Carlo estimate, which reflects all those exploration bonuses, and you take an average of those two. If that makes sense? Or some multi-step return, that also would do. Yeah, that's the thing to keep track. And in both things that we'll see, it's all about novelty. Counting is also about novelty. I want to visit the states that I haven't visited before. Okay, so that's one type of novelty we'll see, and the other is novelty on transitions. Oh, I have never seen this from this state and action to end up in that new state. Now, what you should put there in the place of this exploration bonus, this is what we've seen before from UCB, but any form would do as long as the count increases, the exploration bonus goes down. What we're about to discuss now is a method that generalizes counting to large continuous state spaces, and you will use this form here. So we'll just discuss how to get n with a large continuous state space just now. So we have this general form for the reward. This is cool. Now our exploration bonus depends on the counts of a particular state, yes. The problem is in high dimensions, we rarely visit a state twice. So we cannot just count states. We need to capture a notion of state similarity, and we need to reward the states that are more dissimilar to what we've seen so far. So this is all very simple. As opposed to just being different, because all states will be different from each other. So how we're going to do it? So this is the new thing. We're going to train parameterized visitation density models that tells us how much we have visited a particular state. Okay? What's the probability of this state being in our training set so far, what we've seen so far? Okay, so these states are just going to be images or short sequences of images, for example. Okay? So imagine that we knew how to build such a P theta S. Although this is a big, how to say, research question. given images, how do you assign probability? And the images that are correct and natural, you say high probability, and images that are super weird, you say low probability. So it's the same thing when you have a particular training set. You want to give high probability to images on that training set and low probabilities to images that are maybe natural, but you haven't seen them before. Okay? We're going to use similar generative models of images. Now, if you had such a thing, then you would fit it to the states that you've seen so far. So now every state has a probability. Take a step, observe a new state, you update the model, okay? And you will use the model before and after the transition to estimate the count. And we have these two equations. We say that, you know what, this probability that we assign on that state better equal to these pseudo counts divided by how many states we've seen so far, okay? And so, again, given this fitted p theta prime, once we have a transition, I will design my n hat, this is my pseudo count, so that it satisfies this equation, okay? That is how we would generalize counting in this case. Now imagine we have those probabilities, right? So if existed the notion of pseudo count, that is the equation that it would satisfy, right? The probability of a state is how many times you've been in that state divided by how many states you've seen so far. Okay, this is very simple. So that's it. This is the equation you would get. And then the only thing you do is you fit this in your exploration bonus equation, which is this. And then you add this to your extrinsic reward, and you apply your model-free algorithm. Yes?
How do you ensure smoothness, like states that are close to each other have similar, like, yeah?
Yes, so you cannot really ensure this, but you choose architectures that are smooth, and you hope that, you know, the probability density that you fit is well behaved, okay? And it will be increasing, let's say, for a particular state if you see it before. And now we're going to discuss about potential models that you can use for such density estimation, okay? Yes, so basically the whole point in the slides is how do you compute this density, all right? Okay, sure. Now, if you manage to compute this density, you will do better, as they show in the paper. Yes, so counting is always good at epsilon greedy. So we want to assign probability to every state. What the authors used was a model that was conditioning every pixel to its local neighborhood and was counting some factors based on some local statistics. But if you would go to design such a thing now, why don't you just pick a model, an image generation model, out of those that are available in the literature? And this is what this paper did, which is, from the same authors, next paper, let's say. So there are state-of-the-art models, let's say. For example, this one is from ICML 2016, was the best paper, received the best paper award in ICML 2016. It's called Pixel Recurrent Neural Network, which will do the following. Starting from nothing, they can generate an image by sampling one pixel at a time, and sampling condition on a partial image, they can complete it. Again, sampling one pixel at a time, okay? So let me put this in a context. So first of all, let me start by saying that there is generating images, okay, is a very active area of research right now. Some models, interestingly, some models care about generating beautiful samples, but you cannot really use them to assign probabilities. Interestingly, we care to assign probabilities right now, okay, as we saw in the previous. We don't care about being beautiful, generating beautiful samples or generating fast, etc. GANs and VAEs, as you see, they can generate good samples. They're fast to generate, but they are not easy to use to estimate log likelihood. And autoregressive models, these are models that essentially generate an image one pixel at a time. They're easier to estimate densities, but they're much easier to train, they're much more stable to train, but they don't generate very beautiful samples. Now, GANs, we're going to see when we're going to discuss about imitation learning, because we'll discuss about generative adversarial imitation learning, so we will talk about this technology at that point of the lecture. VAEs we may see later in this lecture, for those that do not know. Yeah, let me not go into detail. However, let's go into some details in the autoregressive model just to see how simple they are. Yes, we want to compute probabilities. We don't care to generate beautiful images right now. So this is how GANs AVAs work. They take a set of noise vector, and they feed it into a huge feed-forward neural network to generate an image. All right? All at once. Now, autoregressive models, they don't do this. They generate one pixel at a time. And the most interesting thing in that model when it came out was that conditioned on all the pixels so far, okay, when you're about to sample the next pixel, that was a softmax out of 255 values. While all previous models were using essentially regression, they used classification. Since you have 255, your pixel value 255. Okay? Now, the truth is that later than this, there was another paper that said you don't need to go into softmax, there's other ways. But in any case, that was very interesting. You just multiply softmax, essentially. That's all you do. Okay? Now, how do you... first of all, let me say, why is it so difficult to build a good generative model for images? Pixels have so many interdependencies. You do need to capture all those interdependencies. Okay? And... these models capture them because they go to these abstract latent variables that potentially say, okay, maybe there should be an animal, and this should be a dog, and a cat on the left, etc., and progressively through the layers of the network generate the image. Here, we'll generate every pixel, we'll condition on whatever we generate so far to generate the next pixel, okay, from those softmaxes. And that's what we're doing. We're saying, using the Bayes theorem, we build a sequential model. And now you may imagine what is the first neural architecture that comes in mind to essentially realize this equation. An LSTM, a spatial LSTM, all right? So you share weights. As you have, let's say, to generate 300 by 300 pixels. To generate each pixel, you're using the same weights on your neural network. The only thing that changes is your conditioning, okay?
Order matter?
The order matters quite a bit because depending on the order, the dependencies that you're going to capture change. Okay, so we'll show different LSTMs with different orderings that capture different. So the standard spatial LSTM goes like that. You estimate for one at a time. You take into account what you generated before and up, and you generate the next. One pixel at a time. This is unfortunately too slow because you cannot parallelize. You need to generate one pixel, right? You need, so the guy down to the left needs to wait everybody above him to be generated for him to generate, right? So that's the problem. Okay, no parallelization, one pixel at a time. So that's pretty slow. Here is a softmax that I told you, which was nice. They treat pixels as discrete variables. So once you are to generate a pixel, conditioning whatever huge hidden state you have, you just sample from a softmax. Okay, you parameterize the softmax. So it looks something like this. Raw LSTM. So now we're going to sacrifice some interdependencies for the sake of parallelization. Instead of generating any pixel at a time, we're going to generate a whole row at a time. So this means that me and the guy next to me, but we're in the same row, we cannot condition on each other. We're just going to condition on the people behind us that have already been generated. And the generation will continue row by row. I don't think this is important for you to know. I just want to say that, look, we have wonderful density models. Instead of using GANs or VAs that are hard to estimate densities, we can use autoregressive and to estimate counting. That's all. So this is a raw LSTM. So you put it here. Now there's a diagonal LSTM. You generate pixels in that order, okay? Now to be able to generate this and this at the same time, they did some rearrangement to be able to parallelize the pixel generation across the diagonals. And eventually what won is the pixel CNN because it's much faster. So what you do is, again, you have a CNN. The problem with the CNN is you have a filter kernel, right? So this means you condition all around you. The problem is that the thing all around has not been generated yet, so you better mask this convolution. So there are these masks that you're going to be using to only have non-zero values in your mask on pixels that have already been generated. Okay? And that's it. And here is the different three architectures. The three different architectures, and it says it's very slow because the more dependencies, fastest, worse look likelihood. Oh well, worse look likelihood. We need to use it because it's the fastest. Log likelihood is how likely you made the images that you had. This is what we're optimizing for. And in general, pixel, if you have better density, you will do better, okay? So for example, here in that particular image, you see that if you use pixel CNN, you have higher score than using the more naive CTS model of that original paper. Importantly, this is what pre-processing you do. So this is how your images look. You downsample them, you make them grayscale, and this is what you fit on your model, okay? Because otherwise it would be too big. And this is what the CTS generates, and this is what the pixel CNN generates, which is a little bit more accurate, let's say. Now, let's go to another approach, which is so simple to generalize counting in high dimensions. They say, why don't we do hashing? Why don't we take images, compress them, okay, and then use this compressed code as a code for a hash function, and we just do approximate counting using hashing. And now the most important question you need to ask is how we're going to compress the images. Well, you can just use an autoencoder, okay? Like what you see here. We take an image and we go to this tiny little bottleneck, okay, which will be the code for the image. We'll decide which bin will count towards. And then from this bottleneck, you need to generate again back the image. And as you see, you have a softmax. Here is again the sampling of the pixels at the very end. Okay? Now, what is the problem with this? The problem is that two images may have extremely subtle changes that are important for your policy. Let's say there's a person holding a knife. If you just compress the two images, this knife will disappear. Why? Because this autoencoder has nothing to do, the autoencoding loss is just reconstruction. You get good loss, low loss, okay? Your objective goes high. Once you are able to reconstruct most of the pixels well. So if most of the background you reconstruct here the carpet well, you're kind of good. I'm just so tiny on the carpet. Does this make sense? So overall, yes, it sounds good, but things break once you try to do these naive solutions. All right? Yeah, now you're going to say, why do we put explicit attention over objects, right? Which is we humans have a very strong bias towards objects. And that's a very good question. And we're going to have potentially next week lectures on transfer learning and what architecture should we be using. And we will discuss about all these biases that we can incorporate. Yes?
If you're already doing like the image processing while playing the game, couldn't you just use the state vector that you like produce from doing that? Because then you would imagine that that would have the information you need since you're using it to make decisions about what actions to take. And then do deep hashing that way rather than just like naively. Because then you're like your weights for processing the image are based off of your actual play of the game rather than.
So what you're saying is, why don't you take your Q function that you're training, that in any how it takes S, the state as input, for example, right, and goes to some bottleneck, and why don't you use this as your hash?
Yeah, exactly. Like the state that you're generating before you, the state that you're inputting to the Q function.
Mm-hmm. So what you're saying is, how can we make this encoding more relevant to our objective, let's say, okay, which is approximating Q values of the policy being correct or something, and why don't we just use the weights of the Q that we're training?
Yeah, basically. Maybe not that like the output of the Q function, but some intermediate state after you've done the initial.
Right. The problem is that this Q potentially doesn't know anything about new states, right?
Okay.
It doesn't know anything about new states. Let me think. Because, okay, one second, let's go back to this question once we see how they use these autoencoders exploration bonds.
Okay.
In 1 second. So here is deep hashing. This autoencoder is going to come back when we talk about transition dynamics, and then we'll discuss more. So yes, if you use TRPO, trust region policy optimization, we discussed about this, and you just add this autoencoder hash, then you do well. And they say, look, it's better to train autoencoder than to take the pixels and hash the pixels. I mean, of course, hashing the pixels themselves directly is a very low baseline. I mean, does this make sense? Of course, we need to go to some latent space where things have been compressed to feed them in the hash function. Now, we've discussed about counting. That's what we've seen, okay? And yes, we discussed about two ways of generalizing counting. Both of them, both fitting and density of the images you've seen and training autoencoders are not related to your objective. So both of them suffer from the fact that they may not pay attention to the very subtle differences that make frames differ from each other of what you need to do when you see them. So this problem remains here, so let's just keep it in our minds. Now, in the next chapter, okay, we're not going to do state counting. We're just going to build a model of the world. What is the model? When we talk about model, we meet about the transition function, the next step function. And we'll have agents that build this internal model, okay? And they will explore, guided from a desire to improve this model. I want to explore so that this model of the world I have in my mind improves the fastest, okay? So to understand this intuitively, potentially if I already know what happens exactly, my transition function, what should do in this part of the space better, I need to explore a different part of the space, because if I take the same tuples, I'm just going to generate zero gradient signal. I already know here how to predict. And building mental models of the world is something well known. Here is Kenneth Craig advocating mental models in 1943, saying that organisms carry a small-scale model of the external reality, what can happen. They use it to generate hypotheses and what is the best, etc., etc. And this is the knowledge that you will carry across different games, okay, ideally. Now, you're going to say that one Atari game and the other do not look very similar. In high level, they do. Like, lots of games have monsters. Lots of games have guns. Lots of games have walls that you cannot penetrate through, okay? So the hope is that this model would generalize across different games. In many, many situations, keys better go to doors as opposed to somewhere else, all right? Now, I want to tell you, models will come back when we talk about model-based reinforcement learning, how we enroll a model to evaluate it. Right now, we're not doing this. We're just using a model, the transition dynamics, to explore, to feed the model and essentially get exploration bonus when this model is not accurate, all right? So we'll use this model more fully in later lectures, okay? Okay, these are two different ways to use the model. Now, a possibility for implementing curiosity and boredom in model building neural controllers. So Jürgen Schmidt-Huber already had advocated these ideas. Now, to be concrete, let's consider transition dynamics, how you will estimate this exploration bonus. You have a lot of choices. You can use the prediction error of your transition dynamics, the norm of the gradient, the information gain regarding your weight distribution. Okay, what does this mean? That you have a Bayesian transition model. There is some distribution theta. A transition comes, next tuple. Once you fit it again to this additional tuple, once your weight have changed a lot, then you have large information gain. If nothing changed, means you already knew about this, nothing has changed. So you're making small learning progress. Or you want to improve your learning progress. And now you're going to say, when these guys are equivalent, isn't it that large prediction error means that I have a large gradient and high learning progress? Do you guys agree with this? Well, it turns out that in stochastic environments, it is not the case. Okay, so I want to say that the model we're building better be, imagine that I'm exploring this CMU environment, the model better be high capacity enough. If your model is low capacity, first problem, low capacity, then no matter how, even if I show you everything about the world, you won't be able to fit it. So all the time you'll have prediction error. Does this make sense? So this assumes that you're training a very big functional approximation for transition dynamics that can fit the world, all right? and that when there is an error, it in fact means not that you have seen this before but you are not able to fit because your capacity is low, but rather because you haven't seen it before. So that's number one. Number two, we will see what happens in stochastic environments. And because it's interesting, I'm just going to keep for surprise. So let's be concrete and start with the simplest thing, which is prediction error. What does this mean? I'm playing Super Mario, and I want to build transition dynamics. What is transition dynamics? I have a state, and I have an action. I hit them in a neural network, and I want to predict the next state. Here, the current state can be the current image or the last 4 images to capture a little bit of the history, and the next state can be the image that comes next. Okay? So Mario jumped. Okay, and then the exploration reward bonus, as we said, is the prediction error. Will be, actually this is wrong, comes from the next. Basically, your transition Ts alpha comma theta minus S prime is exactly your prediction error. Forget about this red equation, it comes from a different slide, it was a copy paste from a different slide. But that's your prediction error. Now you try to fit your model, you try to minimize those prediction errors. Once it comes a state that the prediction is high, okay, then you're happy because you say, oh, I better explore this. Okay, I should explore this. Now, you've seen some states and actions, and you've estimated those exploration bonuses. The idea is that this transition model that you fit from this part of the space generalizes to other parts of the space to tell you when things are novel. So the problem with this very simple training of visual dynamics is that predicting pixels directly is not easy. And usually it fails. I mean, you can use guns and all this fancy machinery, but what people do is instead of predicting images directly, they go to some latent space and they try to train dynamics on that latent space. Okay? To be more compact. You want representations that are compact to learn dynamics easier. Okay, so we'll see how this does as a baseline, but overall we're going to see it doesn't do very well. But here's a transition model that can totally give us some bonuses when the transition error is large, right? For this state, action, next state, tuples. Do we agree? So we'll see the exact algorithm soon. Here is an alternative that you can do. You say that instead of fitting directly the state and trying to, the pixels and trying to predict pixels, I'm just going to encode first my images using this dark red neural network, which is an encoder, and we call it epsilon. It's an encoder and has some weights that are phi. And once you encode, then you're trying to predict the encoding of your next state, essentially. Okay? And you try to minimize I forgot alpha there, which is there. Okay? And you try to minimize the prediction of your network to match the encoding of your future state. Does this make sense? So we have this model that better predicts exactly this. Do you see? So what do you think of this problem, of this optimization? Yes?
So if predicting images is hard,
yes.
Can't we do like the inverse thing where you like have 2 images and then you're predicting the action?
Yeah, excellent. This is the next slide. Just hold 1 second. Hold 1 second. But let's see. Predicting images is hard. Let me tell you. If you predict the action, I see, and use this as your exploration bonus as opposed to what happens next. I see. Well, let me think. First of all, for sure, in this way, you cannot capture things that you cannot control. Okay? So, for example, there are states where I see a lot of interesting students, other students that I cannot control doing some acrobatics out there, let's say, and I find these states interesting. Actually, I haven't thought about this. So we will see this, what you're suggesting as a regularization for our transition model, not as used as an exploration bonus instead of the next state prediction. Does this make sense? But this is good. Let me think. Let's go in the next slide and we'll come back. So what is the problem with this optimization problem? So we said predicting pixels is hard. OK, great. So then let's stick an encoder in front of the images, and let's try to predict the encoding. So now the transition model will take the encoder, will take the action. Well, if you want, you can encode also the action. You put some fully connected. It's not important. Then you combine them, predict the next state. Now this next state, instead of being pixels, is the encoding of the next state. Now if I just write down this problem and I try to minimize jointly both the parameters of my dynamics as well as the parameters of my encoding function, there's going to be a trivial solution coming out. Why?
Because it can map into the same state.
Say it one more time.
So you have the encoder, and the encoder can use some trick to map it.
Right, the encoder can say everything is 0, then you predict 0 from 0, you're good, right? There is nothing that keeps us back to reality, right? That, you know, this encoding better be related to your image. You don't just take an encoder there, okay? Do you see what I mean? There is nothing that, well, before we had something that keeps us back in reality. We had to predict the pixels, okay? So yeah, so that's a problem. People know that this is a problem, and they have proposed solutions. So one is what? We know already the solution. We say we'll use an autoencoder. We'll forget that, you know, this encoding has nothing to do with our loss. And, you know, it's very elegant because now this is what keeps us back in reality, that the encoding, epsilon s phi, better regenerate back the pixels. So if it's 0, there's no way it's going to generate back the right pixels, correct? So now this encoding is useful. So I pre-train phi, whatever is the name of those weights, and then I freeze them when I train my dynamics. Makes sense? It makes sense. Great. Oh, that's cool. Great. So now let's see this in an algorithm to be more concrete. So we observe state, action, next state, reward. Now this reward is the extrinsic reward. Okay? Well, nothing changes in the first line, in line 3. Line 4, let's encode the observations. Okay, great. The only difference here is instead of epsilon, you use the sigma as the encoder. Then let's compute my transition error. So M is the transition model minus the encoding of the next state. And I put L2 square. Okay, great. So you compute your error. And then you create the, as we say, augmented reward, right? That combines your extrinsic reward with your prediction error. All right? Great. So here's your prediction error. We'll discuss about this averaging soon. And then you say, if this is max, I need to update the max because I'm using the max to essentially normalize my rewards. We've discussed about why normalization is important, the same way we had the baseline in that creating and the advantages, the same way when you normalize the bonuses. Because in the beginning, things are going to be crazy novel. Later, they're going to be very tiny. If you don't normalize, these tiny bonuses are not going to be big enough to change your gradient signal. Okay, so it's always good to normalize. We said that this is non-stationary, these bonuses. So we need to do that. And then we say we store now this in our memory bank, which has the augmented reward. Before, in our experience buffer, we're using, you know, the extrinsic reward. Now we're storing the tuples with this augmented reward. Okay. Okay, great. So we pass this, let's say, experience related to any reinforcement learning algorithm, whatever you prefer. Let's say actor critic, or I'm not actually this particular paper. I'm not sure which one it used. And that's it. That's all that happens. Okay. So then, what DRL is going to do? The model-free algorithm will see which states had higher reward, which now is going to be also high exploration, and will bias the policy towards exploring those. The hope is that those that generated high bonus, exploration bonus here, similars will generate similar bonus in the next, let's say, in the next time steps. Does this make sense? You have never seen those unseen states. You've seen some others, okay, that suggested that you need to train your policy towards exploring those, okay? That also made you to explore those others that you haven't seen, of course, before. Does this make sense? It's a little bit weird, right? because before we had task relevant rewards that tells us, yes, we like states, for example, that we're near the heating device, and now whenever you would see heating device, you go there. Now we like states that are novel. Now there may be other states that are novel in different way, okay? It's not clear how much this can generalize from the one that is a novel in a green way to something that is novel in a blue way. Does this make sense? But it for sure generalized to something that is novel in the green way that has generated big the prediction error for you. So this is two things. First, the reward normalization we need to pay attention to. And second, here is the autoencoder. The autoencoder, you may pre-train it and freeze it, or you may be changing it. As you see more data, you update your encoding. Now here's the problem. Once you train a neural network to some inputs where the inputs themselves are changing, you are a little bit in trouble, okay? Because if you're changing the encoding and you're building dynamics that are using this encoding to predict the next state encoding, then this changing encoding will cause trouble to your transition dynamics. Does this make sense? But in any case, you handle it. Essentially, you periodically update this encoding so that you don't create instability, let's say. All right? Okay, so here's another solution that your colleague suggested. That was one solution. One solution was, let's use an autoencoding loss. We know what's the problem with the autoencoding loss. You predict the blue background and you have already extremely low loss. And the tiny little things very hard to encode in that bottleneck. Now here is another way to regularize your problem so that you don't get the trivial solution. It says this encoding phi, that has weights phi, epsilon s of phi, better be so that it should predict the action that given to states, it should predict the action that generated the transition. So this encoding should only care essentially, okay, about whatever the agent can control. Whatever the agent cannot control, since it's not going to help us to infer alpha, will be forgotten from that encoding. So which is great, because this encoding is much more focused, okay? So this sounds like a great idea. And again here, theta and phi are joined on this optimization, and this time we're not going to have the trivial solution, okay, because encoding is stressed out so that it generates the action. We will see how this is doing. This is good. We will join, essentially, we train join forward and backward model. So this was good, but here's the problem. It came another paper that said, even if you just use random weights and you freeze them, and you train dynamics on top of them, you will be okay in Atari games. Now we'll see when you will not be okay, but in any case, do you see the other solution? Forget about phi. Just initialize it and freeze it. And just train dynamics on those random encodings that took your high-dimensional images and made them low-dimensional vectors for you. Random projections. Okay? It's another way to do it. So let's compare them now. And this is the interesting part. We'll compare those setups. The thing that we've been seeing so far is when we have only task reward, extrinsic reward. Then we'll have this intrinsic and the intrinsic bonus that we discussed from the prediction error. And then we'll have extrinsic, but only the terminal. I'm not going to give you intermediate rewards to encourage your behavior. I'm only going to reward you once you are done. You went to the right place of the maze, you finish the game, etc. So much sparser, basically, reward. And the last part, which is the most interesting, is only curiosity. I'm not going to reward you when you finish the game, or when you kill the enemy, or when you save the little cloud or whatever. I'm just going to reward you once you make your prediction, your transition model fail, okay, most. I'm just going to give you bonuses by making you go to states that cause you large prediction error. Okay, so here, well, what do we see here? We see that if you use the curiosity, so there is a line here which is completely at zero, the black one, that is the one that uses extrinsic reward only. So what this says is that if you use curiosity rewards and extremely sparse rewards, you will do much better collecting the normal rewards as if you were training under the normal rewards. Does this make sense to you? So you are not training using the rewards that are going to be tested on. I added this curiosity that has nothing to do with my task. And I ended up having a policy that does very well on getting task rewards. Okay? On, killing the enemies and jumping and... I mean, here there are no enemies, it's just the Unity maze. You need to just go to a lot of rooms in the maze, but... Okay? So this curiosity bonus seems to be doing really well. And the random features seem to be doing as good as using the inverse model regularized features so far. Let's see. Here, now you're going to ask which model-free method did you use? Well, I used A3C, asynchronous actor critic. Okay, in this paper at least that's what they used. And they show that here, and the curiosity shines once you have sparser and sparser rewards. You see the blue curve that A3C trained only with sparse rewards is completely at 0. It's just, yes.
Sorry, finish your sentence.
Okay, let me finish my sentence. So basically, we have here the curiosity is good, and not only curiosity is good, but curiosity that doesn't predict pixels. The predicting pixels is the green, but rather predicting those inverse regularized features is better. Okay, so this transition model in particular is doing better here. Okay, and that's all. I have very interesting videos. Yes.
You said that this was working for the Unity maze, right? I don't know what the Unity maze is, but I imagine that one has a nice reward for reaching the end of the maze. Right? But
There is a reward of reaching the end
the
of
target game may not actually have that much of an interesting reward at the end of the game. It's everything that you did along the way that's interesting, right?
Very nice. Let's go to those Atari games. Let's see what it does in those Atari games. That's a good question. Let's see. So I have some videos. So Visdoom, well, okay, random. So they transfer better to new environments. I want to show you some videos. So, okay, so this is about moving around in the maze. And you see that, we are able to explore much more environments using only the curiosity reward. Okay? Here we're learning to move using only the curiosity reward. Here, I mean, that looks a little bit like an Atari game. Not exactly, but it's the same idea. Just some balls and this guy running around. Only curiosity, okay? And the interesting thing is that when they trained those, so here is Mario. So you train on level 1, and the policy generalizes on a new level, level 3, which has completely different textures. Now I want to say the following. Well, okay, it doesn't generalize. Well, it's jumping. This is good. And this is after fine-tuning. So it's better. So now, once you go to a new environment, instead of starting from scratch, you start from the policy that you trained before. Now, I want to say something. Once you are dead, the way they trained it is when you die, you don't penalize. You just start from the beginning. Eventually, the agent figures out that if I die, I just see the same things. So I should not die. So they are able to go many, many levels, even 10 levels, just guided by curiosity. So curiosity correlates, essentially trying to see more and more and more stuff, correlates well with what the Atari game and whatever video game reward gives you. Yes?
The class behind the class lecture has an exam.
Oh, okay,
So,
sure.
and it's 23.
All right, so we have a big part of this exploration lecture. Probably I'm going to give you next time with a good variational inference type of mini tutorial. Okay? We have to discuss about Bayesian nets for exploration.